We now try a second problem, 3.108, where we have a bead that's mounted on a quarter circular rod. We're told the bead has negligible weight and again slides without friction on the rod. The bead is subjected to a force of magnitude P, yet unknown, that lies in the xy plane and is tangent to the curved rod AB in the position shown. Given that we have a cord that's going to be in tension and is going to exert a force along the line of action defined by C and D, we want to determine the value of P needed for equilibrium in the position shown and find the reaction between the bead and the curved rod AB. Take a moment now to pause this video and try the problem yourself. Resume playing when you're ready to see a solution. Again, our attention is going to be focused on the bead, so I'm going to draw an enveloping surface around that bead to serve as the basis for our free body diagram. I'm going to draw a dashed line which is going to be meant to represent the tangent to the quarter circular arc at C, and P is given as aligned with that, so I'm going to draw P here, and I'll represent it as vector P as scalar magnitude P that we're trying to determine on a unit vector u sub P that we're going to be able to get from the figure, given that P is tangent to the quarter circular arc AB at C. We're also going to have a tension in this cord. So we're cutting through the cord here. It will have a tension in CD that I'll represent as a scalar magnitude on a unit vector that points from C to D, and that we'll be able to get from the geometry of the figure. Finally, we're going to have two reaction forces from the quarter circular rod. Again, it's important that the rod slides without friction, so we're not going to have any resistance to moving along the rod, but we will have two reaction components perpendicular to that tangent. And in this particular case, it will not be that difficult to come up with two directions. So I'm going to end up solving this problem two different ways. One where I have the reaction forces explicitly represented and we solve for them. And then there will be another solution approach where I take advantage of the fact that I know those reaction forces are normal to the rod at C, and I'll be able to get rid of them to simplify my solution. For now, I'm going to draw a reaction force R1 and another reaction force R2, and we'll talk about how to get those in just a minute. So for solution 1, I'm going to actually represent the reactions R1 and R2 explicitly. We're given that this quarter circular rod AB lies in the xy plane, so one of the things we can do that will give us a reaction that's perpendicular to that quarter circular arc is to say that R1 is a magnitude R1 on a unit vector that is perpendicular to that quarter circular arc, and that would be in the k direction. So this would be one acceptable representation for one of those reaction force components. And then the second reaction component will have to be perpendicular to both the quarter circular arc and the first reaction component, and that will be satisfied for a quarter circular arc by picking a second reaction direction that goes just in the radial direction, and we actually have in the figure what that orientation is from the 3, 4, 5 triangle that's shown there. So we'll write vector R2 as unknown magnitude R2 on a second unit vector, and that will end up being 3/5 I plus 4/5 J. We also know that the force P lies in the xy plane and is tangent to the curved rod, and so we know that in a plane, a line of action that's perpendicular to that radial direction is going to have a slope That's the negative reciprocal of the slope shown in the radial direction from O to C. And so we can write that force vector P is P on this unit vector u sub P, but that will be equal to minus 4/5 I plus 3/5 J. Now the last thing we have to do is to represent the tension in the chord, and we'll be able to get that from the geometry of the figure. So let's just first note that the position of C can be found from the radius of this quarter circular rod. Again, on the unit vector that goes from E to C, and that's 3/5 I plus 4/5 J. And so that's 90 I plus 120 J millimeters. It's also the case from the figure that the position vector to D is equal to 150 millimeters in I plus 120 millimeters in K. And so the position vector from C to D is RD minus RC, and that's equal to 60 millimeters in I minus 120 millimeters in J and plus 120 millimeters in K. So this is one of these position vectors that has a magnitude that works out very nicely. The magnitude of RCD turns out to be 180 millimeters. And so that gives us a unit vector that points in the direction from C to D that's equal to 1/3 I minus 2/3 J plus 2/3 K. Finally, we also know the magnitude of the tension in CD because we're given it has an unstretched length of 100 millimeters. And so the tension magnitude is just K times delta, and that's 2 newtons per millimeter times 180 minus 100, and that turns out to be equal to 160 newtons. So now at this point we have all the information we need to write 3 scalar component equations and solve for R1, R2, and force magnitude P, and then we can reconstruct a net reaction force as just the vector sum of R1 and R2. So in the x direction we have 3/5 R2 minus 4/5 P plus the contribution from the tension, which in this case is 160 over 3 equals 0. And this is going to have units of newtons, and we'll call this equation 1. In the y direction, we have 4/5 R2 plus 3/5 P minus 320 over 3 equals 0. And finally, in the z direction, we have just the reaction force R1 plus 320 over 3 equals 0. Now we could call that equation 3, but in this case, what it tells us is that R1 simply has to offset that tension. It's equal to minus 320 over 3, or minus 106.7 newtons. So the direction of R1 actually goes in the other direction from what I sketched in my free body diagram. We can solve for the other 2 unknowns by manipulating these first 2 equations. I could, for instance, take 3/4 of equation 1 and add that to equation 2, and doing so would get rid of the term involving P, and what I would end up with is 9 over 20 plus 4/5 R2 plus 40 minus 320 over 3 equals 0. And if I solve for that, I end up getting that R2 is equal to 4/5 times 200 over 3, which gives me 160 over 3 newtons. If we then substitute that value into the first equation, we get 160 over 5 minus 4/5 P plus 160 over 3 equals 0. And we can manipulate that to show that P is equal to 320 over 3, which again is 106.7 newtons. Now I could take these results and get a net reaction force. R equals R1 U1 plus R2 U2, and that's minus 320 over 3 in the K direction plus 160 over 3 times 3/5 I plus 4/5 J. And if I collect those terms, I end up with a value of R that's equal to 32I plus 42.67 J minus 106.7 K newtons. Now we mentioned in one of the examples that we solved as part of section 3.3 that we really did not need to explicitly represent reaction forces, and so what we could do is take advantage of the fact that we could take a dot product between a unit vector, let's say, that's normal to both R1 and R2, and the vector form of the equilibrium equation, and then those reaction terms just go away by virtue of the dot product of mutually perpendicular vectors going to 0. So what that would look like here is, let's go ahead and write down the vector form of the equilibrium equation, and I'm going to take that whole thing and dot it into the unit vector that's aligned with the force P. If I do that, again, the first two terms go away because that unit vector is perpendicular to both R1 and R2, and then UP dotted into P is just going to give us the scalar magnitude of P. So the first two terms go away, the third term just becomes P, and then I'm just left with plus the tension in CD, which I know, unit vector in P dotted into UCD is equal to 0. So that allows me to get P directly. I can now write P is equal to minus the tension in CD, and then this dot product would be minus 4/5 times 1/3 plus 3/5 times minus 2/3. This term in the parentheses ends up being minus 2/3, and I once again get that P is equal to 320 over 3 newtons, or 106.7 newtons. I can then reconstruct R, the reaction force, by moving P and TCD over to the right-hand side of the vector form of the equilibrium equation. That gives me this result, and if I put all that together, I get exactly the same form for R that I had for the first solution. In summary, for problems like this, you can use either solution procedure depending on your preferences. If you've done the problem consistently, you should get the same result no matter how you proceed. But in some problems, solution 1 is easier, and in others, solution 2 is more straightforward.